This module, we take a look at some different ways to balance ionic equations and also to measure and forecast molarity and titrations. In this particular problem, problem 1, predict the precipitate product by the reaction of aluminum nitrate with aqueous sodium hydroxide. So for these problems, you are going to need your solubility chart. Again, you can find those in the OpenStax chapter textbook. There's also a listing in the references and resources section of our class. So aluminum nitrate, we see that aluminum is a +3, nitrate being a -1. Our sodium hydroxide is a -1, sodium is a +1. These are all soluble, so we are in aqueous solution. We take a look at the aluminum hydroxide. Hydroxide is not going to be soluble with aluminum. So we have a solid, plus we have our sodium nitrate, which again will be aqueous. So we balance our equation here. Next thing we need to do after we have this molecular equation is to get the ionic and net ionic reactions. So again, we'll list out all of our different ions. We're in aqueous solution here. Our aluminum is +3. Again, that nitrate is going to be a -1, and we have 3 of those. Sodium is group 1, so it is a +1. And our hydroxide is a -1, and again we have 3 of each of those. Now technically here, the aluminum hydroxide should stay together because it is a solid and it is not going to be dispersed as ions throughout the solution. But we'll look at that at future problems. So for now, we'll just take a look at aluminum being +3 and hydroxide again being -1. So we have all of our various ions that we would have in solution. To get our net ionic equation, we'll look at it again in problem 2 and problem 3. But we would be looking to cross out anything that was no longer unique. And we'll see what we're talking about here in these future problems. But for now, we're just going to cross out the ones on the reactant and product side that don't contribute to our solid. Our aluminum and hydroxide would stay together as a solid, so they would not be ions in the solution anymore. So we'll look at the ions on the reactant side that created our solid product on the product side. And it would have given us aluminum and hydroxide, creating an insoluble aluminum hydroxide. And then again, technically here we would write AlOH3 as our solid. So problem 2, again predicting the precipitate by mixing aqueous solutions of lead 2 nitrate and potassium iodide. We're going to again write the molecular ionic and net ionic reactions. So nitrates, pretty good at being soluble. We have lead 2 nitrate. We have potassium iodide. Both of which are aqueous. We have our lead 2 iodide. And our potassium nitrate. And while generally iodine is pretty soluble, When mixed with lead 2, it is not. So we balanced our equation here. We have our molecular equation ready and available. Next step is our ionic equation. So it is lead 2, so it's Pb plus 2. There's going to be 2 nitrates. Again, these are both going to be aqueous. We also have 2 potassiums and 2 iodines. Again, both of those are aqueous. They're going to combine and form a solid, insoluble lead 2 iodide. And then we will have a potassium ion, 2 potassium ions, and 2 nitrate ions floating in solution as aqueous. And so when it comes to finding our net ionic equation, we're going to look at the reactant side and the product side, and we're going to cross out anything that is present on both the reactant and product side, because those remain floating around in solution. And so if we look on the reactant side, we do see 2 nitrates on both sides. We do see 2 potassiums on both sides. And so I'm going to cross those out, and what we're left with is our net ionic equation, which was the Pb plus 2 plus the 2 iodides, giving us a solid. Moving on to 3, predict the precipitate by mixing aqueous solutions of sodium hydroxide and magnesium chloride. Again, writing molecular, ionic, and net ionic equations. So we're going to do the same practice one more time. Sodium hydroxide, we're going to give the molecular formulas for each of these. Magnesium chloride, magnesium is group 2. So we have a double displacement here. Magnesium, again, group 2, so I need 2 hydroxides. And we make sodium chloride. Balance our equation. And so we have our molecular equation here. Now we make our ionic equation. We have 2 sodiums, again group 1. Obviously these are going to be aqueous, as described in the prompt. You can also check your solubility charts. We see magnesium hydroxide is not soluble. Back to our ions, we have 2 hydroxides. Of course these are aqueous. We do have a magnesium, again it's group 2, so plus 2. Chlorine, being in group 7, will be a negative 1. We have 2 of those. So they react and they form an insoluble magnesium hydroxide. we do still have sodium floating around in solution. So 2Na+, it is aqueous. We have 2 chlorines. They are aqueous as well. So again, we look at reactant and product side and cross out anything that is not unique. So anything that appears on both sides, we cross out. We have our aqueous sodium, our aqueous chlorine. Both of those are going to be present as reactants and products. So I can cross those out from our ionic equation. And then we have our net ionic equation. Put our cation first here. We have our magnesium +2. It's aqueous. We have 2 hydroxides. -1. It's aqueous. They're combining and forming an insoluble magnesium hydroxide. And there's our net ionic equation. Problem 4, write the molecular ionic and net ionic equations for the following reaction. Same deal as we've just done. Hydrobromic acid. Remember, if it's hydro, it's going to be the H plus the group 7. So think of hydrochloric acid. In this case, it's hydrobromic acid, hydrogen bromine, plus barium hydroxide, barium being in group 2. They're going to combine and form something. Well, we have double displacement here, and it's usually the case with an acid-base reaction. You end up with water plus something, usually some kind of salt. In this case, we have water and barium bromide. So we balance our equation, and we get our molecular equation here. We have aqueous hydrogen bromide or hydrobromic acid. We have aqueous barium hydroxide. We have a liquid, which we usually denote as a cursive L, and H2O, and then we have our aqueous barium bromide. And so our ionic equations, we have 2 hydrogens, group 1. It's aqueous, obviously, and then we have our 2 bromides. They're going to be aqueous. So hydrogen, bromine, we have our barium, group 2, so +2, our hydroxide, polyatomic ion. It's aqueous. They're going to react. They're going to form 2 H2Os, which don't need to be in parentheses here, but we're going to denote that they are a liquid. They are not individual ions in this particular equation. Plus our barium and our bromine, which we have 2 of. So again, we cross out anything that is not unique, as long as it appears on both the reactant and product side. We can cross it out. So bromine appears on both sides. Barium appears on both sides. But our hydrogen and our hydroxide are unique, as is our H2O, our water molecule here. And so now we have our net ionic equation. Two aqueous H pluses and our two OHs, which are also going to be aqueous. They reacted and they formed two H2Os in a liquid state. So molecular ionic and net ionic equations. And we'll do the same thing for part B. Part B has us look at sulfuric acid and potassium hydroxide. And remember that if it is hydro something, it is just H and one element. But if you don't start with hydro, your acid is going to have an H, and then usually some kind of ate. So like a carbonate, or in this case a sulfate. So our ic, sulfuric, means that we have a sulfate in our hydrogen. We have balanced equation. Sulfate's a -2. Hydrogen is a +1. Our potassium hydroxide, potassium from group 1. Hydroxide is a -1. So I'm kind of cheating here and throwing all of our little ions in here, but this is helping me and hopefully helping you figuring out how to do the double displacement in our reaction. And we're seeing that we're swapping the H and the OH to make our H2O, and we are swapping the potassium and moving it over with the sulfate. And we need to account for the charges here so that we know what potassium sulfate would look like. Potassium with our +1 and our sulfate with our -2 means we're going to need 2 of those potassiums to every 1 sulfate. We'll balance the equation. Since I used 2 potassiums on the product side, I needed 2 potassiums on the reactant side. To take a look and make sure we have enough hydrogens. We have 4 on both sides, we look good. 6 oxygens, we look good. So we're going to denote now that we have aqueous sulfuric acid, aqueous potassium hydroxide, aqueous potassium sulfate, and liquid H2O. So we'll write our technical ionic equation here. We've done most of the pre-work for that already. We had 2 hydrogens, we had a sulfate. Hydrogen again was +1, sulfate was -2. You can get these from your polyatomic ion sheet if you need to. The group number denotes the cation charges. And so we know we are dealing with aqueous reactants, and we had our 1 liquid product. The others are aqueous, so we can cross out anything that is not unique. It appears on the reactant and product side. We're left with our net ionic equation of 2 hydrogens that are aqueous, 2 hydroxides that are aqueous, and 2 H2Os that are liquid. Problem 5, how many grams of potassium dichromate are required to prepare a 250 milliliter solution whose concentration is 2.16 molarity? So remembering that molarity is moles per liter, I'm going to check the periodic table and do the work for you here. But the molecular weight of potassium dichromate is 294.2 grams per mole. So with that in mind, we're looking for how many grams of potassium chromate are required to prepare this molarity of solution, and only 250 milliliters of this solution. So milliliters are not going to be very conducive since I need moles per liter, so I'm going to convert that into liters. Move the decimal over 3 times or divide by 1,000. 250 milliliters is 0.250 liters. And so I'll start with getting rid of my liters and getting into moles. So I want to know how many moles of potassium dichromate I need to have. And then the prompt asks me for how many grams I need to have. So I'm going to get rid of moles and convert it into grams. So my given was 250 milliliters of a concentration, 2.16 molarity. I started with my volume. I used my molarity to convert into the amount of potassium dichromate, and then I could convert the moles, that amount of potassium chromate, into actual grams. And I really only have 3 significant figures here. At best, I may only have 2, looking at that 250 milliliters. But if we assume that I had 3, we're looking at about 159 grams. Since there's no decimal after that 250 milliliters, I probably only had 2 significant figures to work with there. Problem 6, calculate the molarity of an 85 milliliter ethanol aqueous solution containing 1.77 grams of ethanol. So again, I'm looking to get moles per liter here since I'm calculating molarity. My given is 1.77 grams. So the first thing I'm going to do is get out of grams and get into moles. So I'm given 1.77 grams. Ethanol has a molecular weight of 46.07 grams per mole. So now I know I'm dealing with 0.0384 moles. I have 0.0384 moles in my 85 milliliters. Convert that to liters. We get 0.0850 liters. Moles per liter is going to give me a molarity of 0.452 moles per liter, or 0.452 molarity. There are other ways that you can calculate this, but I'm trying to make it as easy to follow as possible here. Problem 7, what volume in milliliters is a 0.315 molarity sodium hydroxide solution that contains 6.22 grams of potassium hydroxide? They tell us that we have a 0.315 molarity solution, so we know that we're dealing with 0.315 moles per liter. Our given is grams. Grams doesn't help us, so we need to get into moles. So we take our 6.22 grams of potassium hydroxide. We convert that into moles. Potassium hydroxide is 40.0 grams per mole. Since they want volume and they want it in milliliters, I need to get out of moles and into liters. So I'm going to use our molarity. And since I'm going to try to get rid of moles, I need to put moles on the bottom. 0.315 moles per 1 liter. And remembering that the prompt asks for volume in milliliters, so I need to get out of milliliters, out of liters and into milliliters. So I double check my units. Grams will be eliminated, moles will be eliminated, liters will be eliminated. I'm left with milliliters, and that's what the prompt asked for. We calculate, and we get 493.6, but I should only be in 3 significant figures. So 494 milliliters of sodium hydroxide. Problem 8. Describe the preparation of 500 milliliters of 3.35 molar lithium hydroxide solution. So it's not just enough here to necessarily calculate it, but they want us to be able to describe how to prepare this solution. So remembering that we have moles per liter, so there's a couple of things that we could do here to describe this preparation. But basically we're making a half of a liter of 3.35 moles per liter solution. So the first thing we're going to do is figure out, okay, well, how much lithium hydroxide do we need? Get out of the milliliters, convert it to liters. And then we use our molarity to get into moles. And then I need to convert from moles to grams. And so we look up on the periodic table and we find out that lithium hydroxide has a mass of 23.95 grams per moles. So now we're going to figure out exactly how many grams here we should be looking at in order to create this 500 milliliter solution. And to 3 significant figures, we have 40.1 grams of lithium hydroxide. So if I was describing how to prepare the solution, I would say I'm taking 40.1 grams of solid lithium hydroxide, and I'm going to add distilled water to it until I reached 500 milligrams. Problem 9. Calculate the molarity of 5.00 liter solution containing 69.3 grams of potassium hydroxide. So again, molarity is moles per liter. I need to get out of grams and into moles. So 69.33 grams potassium hydroxide. Potassium hydroxide has a mass of 56.11 grams per mole. I find out that I'm working with 1.24 moles. And now for density, I'm going to divide that by the given 5 liters of solution. And now I have moles per liter, which is our molarity. I get 0.247 molarity, or 0.247 moles per liter of potassium hydroxide. Problem 10. How would you prepare 200 milliliters of 0.866 molarity NaOH solution, starting with a 5.07 molar stock solution? So we're going to use our formula of M1V1 equals M2V2. I start with, given here, of 200 milliliters, so I have three significant figures. I convert that into liters since molarity deals with moles per liter. So I know that I'm dealing with 0.200 liters of our sodium hydroxide. So M1V1, I have 0.866 molarity times 0.200 liters. Our second solution here is 5.07 molarity times our unknown volume. I solve for V2. Says I need 0.0342 liters of this solution. So how would I prepare 200 milliliters? What I'm going to do is I'm going to take 0.0342 liters, or 34.2 milliliters, of the 5.07 molarity solution, and I'm going to pour that into enough water to reach 200 milliliters. And so if you can envision our beaker here of 5.07 molar stock solution, or very highly concentrated solution, I need to get to 200 total milliliters of solution, or 0.200 liters. And so I'm going to take my secondary container, or my little beaker here that I've tried to draw, which I'm terrible at drawing, as you can tell. But I'm going to first fill it with water because I drop acid into the water. So if I needed 200 milliliters, I would subtract how much of my stock solution I'm going to pour in there, which was 34.2 milliliters. I find out that I'm going to need to add 165.8 milliliters of water first, or in three significant figures it would have been less, except for we're dealing with addition and subtraction here, so I'm going to look at decimal places. 165.8 milliliters first of water, then I'm going to pour in 34.2 milliliters of our stock solution so that I reach a total of 200 milliliters. And that's going to give me 0.866 molarity. Number 11, consider the acid-base titration of sulfuric acid and potassium hydroxide. This is a strong acid reacting with a strong base. How many milliliters of a 1.28 molar sulfuric acid solution are needed to neutralize 60.2 milliliters of a 0.427 molar potassium hydroxide solution? The first thing I need to do is get a molecular equation and then balance our molecular equation, because I'm going to need some mole to mole ratios here. So we look at our molecular equation here. It's double displacement. I see that I have potassium as a product. I have two of them and only one potassium on the reactant side. So I know I'm going to need an additional potassium there. So I'll use a coefficient of 2 in front of potassium hydroxide. And then I'll worry about balancing hydrogens and oxygens at the end. just to visualize what we're doing here, my original sulfuric acid solution is 1.28 molarity. My original molarity of my base, or my potassium hydroxide, was 0.427. So writing in our balanced equation, we look at the hydrogens here. We have 2, 3, 4 as reactants. Now we have 4 as products. We have 6 oxygens as reactants. We have 6 oxygens as products. 1 sulfur, 1 sulfur. So we look good here as our balanced equation. So we have given molarities here, and we have a given volume. So I need to figure out how many moles I'm working with. I'm given 60.2 milliliters of our potassium hydroxide. I'm going to get that into liters since I'm given a molarity. 1 liter is 1,000 milliliters. My molarity that I'm given here is 0.427. So we want to know how many moles am I actually dealing with here in this solution. Because that's going to tell us how many moles of our sulfuric acid we're going to need in order to neutralize this base. So I'm giving you a second here to calculate that. And ideally to 3 sig figs you'd have 0.0257 moles of potassium hydroxide is what you are currently dealing with. And so now we need to figure out how many moles do we need of sulfuric acid to neutralize our 0.0257 moles of potassium hydroxide. And so this is going to have us analyze our mole-to-mole ratio here. We see that we have 0.0257 moles of potassium hydroxide. We use our balanced equation. We need to get rid of potassium hydroxide, so it's going at the bottom. On our balanced equation, there are 2 moles of potassium hydroxide for every 1 mole of sulfuric acid. We want to get out of moles and get into volume. So we use our molarity. The molarity we were given was 1.28 moles per liter. We're going to calculate this volume into milliliters, so let's get out of liters and into milliliters. Since that's what the prompt has asked for. Multiply across, divide by the bottom. And remembering only 3 significant figures. So I actually got 10.3 milliliters, despite what I wrote there. So hopefully you found this helpful.